Electrons don't have position. The truth, Heisenberg, hid from you. Point to something in the room right now. Anything. A chair, a lamp, your coffee cup. Now tell me exactly where it is. You can do that, right? You can describe its position precisely. 3 meters from the wall, 1 meter off the ground, sitting on your desk. The object has a location. A definite, specific, knowable location in space. That's obvious. That's basic. That's reality. Except it's not. Not at the level that matters. Not at the level where reality actually happens. Because Werner Heisenberg discovered something so disturbing, so completely incompatible with common sense, that it shattered the entire foundation of classical physics. He discovered that electrons don't have positions. Not in the way you think. Not in any way that makes sense to your everyday experience. They simply don't have definite locations in space until you force them to. This isn't about measurement being difficult. This isn't about instruments being imprecise. This is about reality itself being fundamentally different from what you've been taught your entire life. Electrons don't have positions the way your coffee cup has a position. And once you understand why, once you really grasp what Heisenberg proved, you'll never look at the solid world around you the same way again. Let me ask you something that seems ridiculously simple. Where is the electron in a hydrogen atom right now? You learned in school that electrons orbit the nucleus, like planets around the sun. Right. Neat circular or elliptical paths. The electron is somewhere on that orbit. It has a position. It's here. Then it moves to there. Then it moves to the next spot. A continuous path through space. A definite location at every moment in time. That picture is completely wrong. Totally, fundamentally, catastrophically wrong. And Niels Bohr knew it was wrong back in 1913, when he proposed his atomic model. He knew the electron couldn't actually be orbiting because an orbiting charged particle should radiate energy, continuously and spiral into the nucleus in a fraction of a second. Atoms should collapse instantly, but they don't. So something about the orbit picture had to be false. But Bohr didn't know what to replace it with. Nobody did. For over a decade, physicists struggled with this paradox. They knew electrons couldn't be orbiting in the classical sense, but they had no better picture to put in its place. They patched the theory with ad hoc rules. Electrons can only occupy certain orbits. They jump between orbits without traveling through the space in between. The rules worked mathematically, but made no physical sense. It was a mess. An inconsistent, unsatisfying mess. Then Werner Heisenberg came along and said something radical. Stop trying to visualize what the electron is doing. Stop trying to picture its path. Stop asking where it is between measurements. Those questions are meaningless. The only thing that matters is what you can actually observe. And what you observe are discrete jumps. Energy levels changing. Photons being emitted or absorbed. Measurement results, not continuous trajectories. Not definite positions at all times. This was revolutionary. This was a complete break from how physics had been done since Newton. Physics had always been about building mental pictures of what was happening. Planets moving through space. Waves rippling through media. Particles colliding like billiard balls. You could visualize it. You could imagine watching it happen. That's what made physics intuitive. That's what made it feel real. Heisenberg threw that away. He said the electron doesn't have a continuous trajectory. It doesn't have a definite position when you're not measuring it. And trying to imagine what it's doing between measurements is not just difficult, it's wrong. It's asking a question that has no answer. It's trying to apply classical concepts to a fundamentally non-classical reality. And here's where it gets truly bizarre. When you do measure the electron's position, when you actually force it to reveal where it is, you find it at a specific point. The measurement gives you a definite answer. The electron is here, right here, at this precise location. But before you measured it, before you interacted with it, it wasn't anywhere. It didn't have a position. It existed in what quantum mechanics calls a superposition state. A superposition is not a state of ignorance. It's not that the electron was somewhere and you just didn't know where. It's that the electron genuinely didn't have a definite position. It was spread out, Existing as a cloud of probability, rather than a point in space, the position didn't exist until you measured it. The measurement created the position, rather than revealing a pre-existing position. Let me say that again, because it's so important. The electron doesn't have a hidden position that you discover when you measure it. The electron has no position until measurement forces it to have one. Position is not a pre-existing property. Position is something that comes into being at the moment of measurement. Before measurement, there's only probability. After measurement, there's actuality. Measurement transforms possibility into reality. This is what Heisenberg's uncertainty principle is really telling you. It's not just saying you can't measure position and momentum simultaneously. It's saying the electron doesn't have both simultaneously. The properties don't exist together. You can force the electron to have a definite position by measuring position. Or you can force it to have a definite momentum by measuring momentum. But you can't force it to have both, because having both is not a state that quantum systems can exist in. The electron is not a tiny ball flying through space with a definite position and momentum at all times. The electron is a quantum object that can be forced to exhibit position-like behavior or momentum-like behavior, depending on what you measure, but it doesn't have both properties simultaneously. It exists in a state that has no classical analog, a state that can't be visualized using everyday intuition. Now you might be thinking, okay, but this is just about electrons, about tiny quantum particles. My world, the world I see and touch, that's made of definite objects with definite positions. My chair is in a definite location. My cup is in a definite place. Surely this quantum weirdness doesn't apply to everyday objects. And you're right that everyday objects behave classically. Your chair does have a definite position. But here's the thing that should disturb you deeply. Your chair is made of atoms. Those atoms are made of electrons and nuclei, and those electrons don't have definite positions. So how does a collection of positionless electrons add up to a chair with a definite position? The answer is decoherence and the law of large numbers. Your chair contains something like 10 to the power of 27 atoms. That's a 1 followed by 27 zeros, an unimaginably vast number. Each electron in each atom is in a quantum superposition, spread out over space as a cloud of probability. But when you have trillions upon trillions of these probability clouds all overlapping, all interacting with each other and with the environment, something remarkable happens. The quantum uncertainties average out. The position of any single electron is indefinite, uncertain, probabilistic. But the average position of 10 to the 27 electrons becomes incredibly well defined. The statistical fluctuations become negligibly small compared to the size of the object. The chair's position emerges as a classical definite property from the quantum indefinite properties of its constituents. So your chair has a position not because its electrons have positions, but because the collective behavior of vast numbers of electrons produces something that behaves as if it has a definite position. The classical world you experience is an emergent statistical phenomenon arising from an underlying quantum reality that has no definite positions at all. Think about what this means. Every solid object you've ever touched, every stable structure you've ever relied on, every definite location you've ever specified, all of it is built on a foundation of quantum indefiniteness. The solidity is an illusion created by averaging the definiteness, is an approximation that works at large scales but breaks down at small scales. Reality at its most fundamental level doesn't have the properties you think it has, and Heisenberg proved this. Not through philosophy or speculation, but through rigorous mathematical physics. He showed that the equations of quantum mechanics don't allow electrons to have definite positions and definite momenta simultaneously. The position operator and the momentum operator don't commute. They can't both have definite values. It's built into the mathematical structure of quantum theory. It's not negotiable. It's not optional. It's fundamental. Let me show you what this looks like in practice. Take the famous double-slit experiment. You fire electrons, one at a time, at a barrier with 2 slits in it. Behind the barrier is a detection screen that records where each electron hits. If electrons were classical particles with definite positions and definite trajectories, each electron would go through one slit or the other, and you'd see two bands on the detection screen corresponding to the two slits. But that's not what happens. You see an interference pattern. Multiple bands. Light and dark fringes. The same pattern you get when you send waves through to slits and let them interfere with each other. But you're sending electrons one at a time. Each electron is a single particle. It can't interfere with other electrons because there are no other electrons present. So what's interfering? The electron is interfering with itself, because the electron doesn't go through one slit or the other. It goes through both. Simultaneously, it exists in a superposition of going through the left slit and going through the right slit. The electron's position is indefinite. It's not localized to one path or the other. It's spread out. It's a wave of probability that passes through both slits, and those probability waves interfere with each other, and the interference pattern appears on the detection screen. But here's the really mind-bending part. If you try to determine which slit the electron actually went through, if you put a detector at one or both slits to measure the electron's position, the interference pattern disappears. You force the electron to have a definite position by measuring which slit it went through. And once it has a definite position, once it's localized to one slit or the other, it can't interfere with itself anymore. It behaves like a classical particle. The measurement destroys the superposition. This is what Heisenberg meant when he said you can't know position and momentum simultaneously. Measuring position localizes the electron. It forces the probability wave to collapse to a definite point. But doing that necessarily disturbs the momentum. The more precisely you localize position, the more you spread out the momentum. The more indefinite the momentum becomes. You can't have both definite at the same time, because forcing one to be definite makes the other indefinite. And this isn't about clumsy measurement techniques. This is about the nature of quantum systems. The electron in a superposition state genuinely doesn't have a definite position. It's not that it has a definite position, and you just don't know it. It doesn't have one. Position is not a property the electron possesses before measurement. Position is something that emerges when you force the electron to interact with a measuring device in a way that reveals position. Now let's talk about what this means for the structure of atoms, because this is where Heisenberg's insight becomes absolutely crucial. You learned that electrons orbit the nucleus, but we've established that's wrong. Electrons don't orbit. So what are they doing? Where are they? How do atoms work if electrons don't have definite positions? The answer is orbitals, not orbits. Orbitals. An orbital is not a path. It's not a trajectory. An orbital is a probability distribution. It's a mathematical description of where you're likely to find the electron if you measure its position. The electron doesn't travel along the orbital. The electron is the orbital. Its existence is spread out over the entire region described by the orbital. It's everywhere in the orbital simultaneously until you measure it. Take the simplest atom, hydrogen, one proton, one electron. In the ground state, the electron exists in what's called the 1s orbital. This is a spherically symmetric cloud centered on the nucleus. The electron doesn't orbit the nucleus at a fixed radius. The electron is spread out in a sphere. The probability of finding it is highest near the nucleus and decreases with distance. But there's some probability of finding it anywhere in that spherical region. The electron doesn't have a position in the classical sense. It has a wave function. And the wave function tells you the probability of finding the electron at each point in space if you measure its position. Before measurement, the electron exists as this cloud of probability. After measurement, you find it at a specific point. But which point you find it at is random. It's probabilistic. You can't predict exactly where it will be. You can only predict the odds. And here's something that makes this even stranger. When the electron is in this probability cloud state, in this superposition of being at many different positions simultaneously, it's not just position that's indefinite. Energy levels are definite. The electron in the 1s orbital has a specific, well-defined energy, but position is spread out. The electron has definite energy and indefinite position at the same time. This shows you something profound about quantum mechanics. Different properties are definite or indefinite depending on the state the system is in. An electron in an energy eigenstate has definite energy but indefinite position. If you measure position and find the electron at a specific point, now position is definite but energy becomes indefinite. You can't have both definite simultaneously. They're complementary properties. Knowing one precisely means not knowing the other precisely. And this complementarity, this trade-off between different properties, is the core of Heisenberg's uncertainty principle. It's not just about position and momentum. It's about any pair of complementary variables, energy and time, angular momentum components in different directions. The principle is universal. It applies to everything quantum. And since everything is ultimately quantum, it applies to everything, period. But what does it mean to say the electron doesn't have a position? How can something exist without being somewhere? This question tormented physicists for decades. Einstein never accepted it. He insisted there must be hidden variables, deeper properties that determine where the electron really is, even though we can't measure them. The indefiniteness, he thought, was about our ignorance, not about reality itself. But Einstein was wrong. Experiments have proven it definitively. John Bell developed a mathematical theorem in the 1960s that showed local hidden variables can't explain quantum correlations. Then experimenters tested Bell's inequality using entangled particles. They measured correlations between distant particles and found that quantum mechanics was right and hidden variables were wrong. The indefiniteness is real. The electron genuinely doesn't have a definite position before measurement. It's not hidden. It doesn't exist. This is the truth Heisenberg discovered, and that took the scientific community decades to fully accept. Electrons don't have positions in the sense that your coffee cup has a position. They exist in states where position is indefinite, where the property simply doesn't have a value, and measurement doesn't reveal a hidden position. Measurement creates position by forcing the quantum system to interact with a classical measuring device in a way that localizes the wave function. Think about the implications of this for your understanding of matter. You think of objects as being made of atoms, and atoms being made of electrons and nuclei. And you think of electrons as being little particles with definite positions, even if those positions are hard to measure. But that's wrong. Electrons are quantum fields in excited states. They're ripples in a fundamental field that pervades all of space. And those ripples don't have definite positions until measurement localizes them. The atom is not a miniature solar system with electrons orbiting a nucleus. The atom is a nucleus surrounded by probability clouds, by regions where electrons might be found if you look. But until you look, the electrons aren't anywhere specific. They're dilocalized, spread out, existing as waves of probability rather than point particles with definite locations. And this is true for every atom in your body. Every electron in every atom is in this indefinite state. The electrons that make up your neurons, that carry the signals that create your thoughts, they don't have definite positions. They're probability clouds. They're quantum superpositions. Your brain, your body, your entire physical existence is built on a foundation of quantum indefiniteness. Now you might object. You might say, but I feel solid. I have a definite location. I'm here, not there. How can I be made of electrons that don't have positions? And the answer is the same as before. You're made of vast numbers of electrons, 10 to the 28 or so, and the collective behavior of that many electrons produces classical definiteness, even though each individual electron is quantum indefinite. Your position emerges from averaging over countless quantum uncertainties. You have a definite location because the statistical fluctuations in the positions of your constituent electrons are so small compared to your size that they're completely negligible. The quantum world averages out to classical behavior at large scales. But the quantum indefiniteness is still there underneath. It's the foundation everything else is built on. And here's something that really drives home how fundamental this is. The very fact that matter is stable, that atoms don't collapse, that solid objects can exist, depends crucially on the fact that electrons don't have definite positions. If electrons were classical particles with definite positions and definite momenta, they would radiate energy continuously as they orbited the nucleus and spiral inward. Atoms would be unstable. Matter as we know it couldn't exist. But because electrons don't have definite positions, because they exist in these spread-out orbital states, they don't radiate. They're not orbiting, they're not accelerating. They're just existing as probability distributions. And those distributions are stable solutions to the Schrödinger equation. They can persist indefinitely without collapsing. The atom is stable precisely because the electron doesn't have a definite position and a definite momentum simultaneously. So the solid stable world you live in, the fact that matter doesn't immediately collapse into nothing, depends on Heisenberg's uncertainty principle. Depends on electrons not having definite positions. The indefiniteness isn't a weird quantum quirk that only matters in obscure experiments. It's the reason you exist. It's the reason anything exists. Classical physics predicts that atoms should collapse. Quantum physics explains why they don't. And the key is the uncertainty, the indefiniteness, the fact that position and momentum can't both be definite at once. Let me show you another consequence of this that's even more bizarre. Because electrons don't have definite positions, they can do something impossible in classical physics. They can tunnel through barriers. Take an electron approaching a barrier, a region where classically it doesn't have enough energy to pass through. In classical physics, the electron bounces back. It can't penetrate the barrier because it doesn't have enough energy. But in quantum mechanics, the electron's position is indefinite. It exists as a probability wave. And probability waves don't stop abruptly at barriers. They decay exponentially inside the barrier. But they don't go instantly to zero. There's some probability, however small, of finding the electron on the other side of the barrier, even though classically it couldn't have gotten there. And this isn't theoretical. This is measured reality. Quantum tunneling happens constantly. It's how nuclear fusion works in the sun. Protons don't have enough energy to overcome the electromagnetic repulsion and collide. But they tunnel through the barrier. Their positions are indefinite enough that there's some probability of being much closer than classical physics allows. And that makes fusion possible. The sun shines because protons don't have definite positions. Quantum tunneling is also how scanning tunneling microscopes work. You bring a sharp tip very close to a surface. Electrons tunnel from the surface to the tip, or vice versa. The tunneling current depends exponentially on the distance. So by measuring the current and moving the tip around, you can map out the surface with atomic resolution. You can see individual atoms. And it works because electrons don't have definite positions. They tunnel through gaps that classically they couldn't cross. And here's something that should blow your mind. Radioactive decay happens because of quantum tunneling. An alpha particle inside a nucleus doesn't have enough energy to escape. It's trapped by the nuclear force. Classically, it should stay trapped forever. But quantum mechanically, its position is indefinite. There's some probability of finding it outside the nucleus, even though it doesn't have enough energy to get out. And eventually, randomly, it tunnels out. The nucleus decays, and when it will decay, is completely unpredictable. It's fundamentally random, determined only by probability. So radioactivity, one of the most important phenomena in nuclear physics, happens because alpha particles don't have definite positions. If they had definite positions and definite energies, if they obeyed classical physics, nuclei would be either stable or instantly unstable. There would be no slow radioactive decay. The fact that decay happens at random times over long periods is direct evidence that particles don't have the definite properties you think they do. Now let's connect this back to Heisenberg and the historical development of quantum mechanics, because understanding how this was discovered makes it even more remarkable. In 1925, Heisenberg was 23 years old. 23. He was working with Max Born and Pascual Jordan, developing a new mathematical framework for quantum mechanics called matrix mechanics. And the math was strange, abstract, non-intuitive. The key insight was that observable quantities like position and momentum couldn't be represented by ordinary numbers. They had to be represented by matrices, and matrices don't commute. The order matters. Position times momentum gives you a different result than momentum times position. The commutator, the difference between the two orders, is non-zero. And that non-zero commutator directly implies the uncertainty principle. Heisenberg realized that if position and momentum don't commute, if they can't be measured simultaneously without disturbing each other, then there must be a fundamental limit on how precisely you can know both. He worked out the mathematics and derived the famous inequality. The uncertainty in position times the uncertainty in momentum is greater than or equal to Planck's constant divided by 4 pi. This wasn't a guess. This wasn't a philosophical musing. This was rigorous mathematics falling directly out of the structure of quantum theory. And when Heisenberg published this in 1927, it caused a sensation, and also a lot of confusion and resistance. Even Niels Bohr, who had mentored Heisenberg, initially disagreed with his interpretation. Bohr thought Heisenberg was focusing too much on the disturbance caused by measurement. Bohr wanted to emphasize complementarity, the idea that wave and particle properties are complementary aspects of quantum objects. The two men argued passionately. The debates were intense, emotional, sometimes bitter. Eventually, they reached a synthesis, the Copenhagen interpretation of quantum mechanics. But the core of Heisenberg's insight remained. Electrons don't have definite positions and definite momenta simultaneously. Not because we can't measure them precisely enough, but because the properties don't exist simultaneously. The electron in an atom doesn't have a trajectory. It doesn't orbit. It exists as a cloud of probability described by a wave function. And position becomes definite only when measurement forces it to. This was revolutionary. This overturned 300 years of classical physics. Since Newton, physics had assumed that objects have definite properties independent of observation. An apple falling from a tree has a position and a velocity at every moment, whether anyone is watching or not. The universe was made of things with properties. And physics was about discovering what those properties were, and how they changed over time. But Heisenberg showed this is wrong at the fundamental level. Quantum objects don't have all properties at all times. Some properties are definite, others are indefinite, depending on the state of the system. And measurement doesn't just reveal pre-existing properties. Measurement participates in creating the properties by forcing the quantum system into a state where that property has a definite value. This is why Heisenberg's discovery was so disturbing. It wasn't just a new theory about small things, it was a complete reconceptualization of what it means for something to exist, to have properties, to be real. Classical physics said reality is made of objects with definite properties. Quantum physics says reality is made of potentialities that become actualities through measurement. The philosophical implications are staggering. And these implications extend far beyond physics. If electrons don't have positions until you measure them, what does that say about the nature of reality itself? Is reality observer dependent? Does consciousness play a role in collapsing wave functions? These questions remain hotly debated. There are multiple interpretations of quantum mechanics, each trying to make sense of what measurement means and what happens before measurement. But what's not debated, what's established beyond any doubt by countless experiments, is that Heisenberg was right. Electrons don't have definite positions and definite momenta simultaneously. The uncertainty principle is as well verified as any principle in physics. It's been tested in every imaginable way, and it always holds. The universe really does have this fundamental limit on knowability. Reality really is indefinite in ways that violate classical intuition. And this brings us to something absolutely crucial about modern technology. The entire electronics industry, every computer chip, every smartphone, every digital device, depends on quantum mechanics. Depends on the fact that electrons don't have definite positions. Transistors work because electrons can tunnel through barriers. Semiconductors work because electrons exist in energy bands with indefinite positions. None of our modern technology would be possible if classical physics were correct. Quantum mechanics isn't just some abstract theory about things too small to matter. It's the foundation of the modern world. Every time you use a computer, every time you use GPS, every time you use any electronic device, You're relying on technology that only works because electrons don't have the definite positions you think they should have. The quantum weirdness is not philosophical, it's practical. It's the reason your phone works. And emerging technologies like quantum computing take this even further. Quantum computers exploit superposition. The fact that quantum bits can be in indefinite states, neither 0 nor 1 but both simultaneously. This allows quantum computers to perform certain calculations exponentially faster than classical computers. The indefiniteness isn't a limitation to overcome. It's a resource to exploit. The uncertainty is the feature that makes quantum computing powerful. So, when you really understand what Heisenberg discovered, when you grasp that electrons don't have positions in any classical sense, you realize this isn't just trivia about tiny particles. This is fundamental to the nature of matter, to the stability of atoms, to the existence of solid objects, to the technology you use every day, to the very possibility of complex structures, like your body and your brain, existing at all. The world you see and touch feels solid and definite because you're made of trillions upon trillions of quantum particles, and the collective behavior averages out to classical definiteness. But underneath, at the most fundamental level, everything is probability clouds. Everything is wave functions. Everything is indefinite until measurement forces it to be definite. And that indefiniteness, that quantum uncertainty, is not a bug. It's what makes reality work. Heisenberg discovered this when he was barely out of graduate school. He worked out the mathematics, published the Uncertainty Principle, and changed physics forever. And he did it by abandoning visualization, by giving up on trying to picture what electrons are doing, by focusing only on what can be measured. That was his genius, realizing that the pictures were wrong and needed to be thrown out. That reality at the quantum level is fundamentally not. And here we are, a century later, and we still struggle to accept it emotionally, even though we know it intellectually. We still want to think of electrons as little balls with positions. We still want to visualize atoms as miniature solar systems. Our intuition, built by evolution to navigate a macroscopic classical world, rebels against the quantum truth. But the rebellion doesn't change the facts. Electrons don't have positions, and Heisenberg proved it, forever. So the next time you look at an object and think about where it is, remember what's really happening. That object is made of atoms. Those atoms are made of electrons and nuclei. Those electrons don't have definite positions. They're probability clouds. They're quantum superpositions. They're waves of potentiality. And the definite position you perceive is an emergent property, a statistical average, an illusion of solidity created by vast numbers. Reality, at its foundation, is not solid. It's not definite. It's not made of things with locations. Reality is made of quantum fields in excited states, of probability distributions, of wave functions that collapse when you measure them. And position, that most basic property you take for granted, doesn't exist until measurement creates it. That's the truth Werner Heisenberg discovered. That's the truth that destroys classical physics. That's the truth you can never unknow once you understand it. Electrons don't have positions. And now you know why. Because quantum mechanics says so. Because the mathematics demands it. Because experiments verify it. Because reality at its most fundamental level is probabilistic, indefinite, non-classical, and the solid, definite world you experience is built on a foundation that has none of those properties. That's not a limitation of our knowledge. That's the nature of existence itself, and Heisenberg figured it out. At 26 years old, forever changing how we understand reality. If this revelation has shattered your understanding of matter and position, if you're seeing the solid world with completely new eyes, then you're ready for more. Subscribe to this channel right now and activate notifications because we're exploring the deepest mysteries of quantum reality with the same clarity and intensity that Werner Heisenberg brought to physics. Hit that like button if this video destroyed your classical intuitions. Share it with someone who still thinks electrons orbit like planets, and leave a comment telling us what shocked you most. Was it that position doesn't exist before measurement? That atoms are stable because of uncertainty? That your body is built on indefiniteness? Your engagement builds our community of people ready to face the truth about reality, no matter how strange it is. Remember, the greatest gift Heisenberg gave us wasn't just the uncertainty principle. It was the courage to accept that reality is fundamentally stranger than we can imagine, and the intellectual honesty to follow the mathematics wherever it leads, even when it destroys our intuitions. That courage, that honesty, that willingness to abandon comfortable pictures in favor of uncomfortable truth, is what we celebrate in every video. The universe is not what it seems. Electrons don't have positions, and understanding why changes everything. Until the next revelation that explodes your reality, we'll see you in the next video, where we continue unraveling the quantum fabric of existence, one mind-bending truth at a time.